Greetings. The easiest way to understand an operation like graphical vector addition is to see it in a problem. So this is a problem in which we can use graphical vector addition to determine the motion of an airplane. We have an airplane that can move 200 miles per hour in still air. It's moving 30 degrees east of north, which is in this direction, runs into a headwind of 50 miles per hour that is 20 degrees south of west, which is in this direction. And the question is, what is its net motion? As I said, there are two vectors involved, one having to do with the velocity generated by the plane's engine, the other having to do with the velocity generated by the headwind. If we add those two together graphically, vectorially, we will come up with the net resultant velocity, which will identify the motion. First thing you have to do in a problem like this is to identify the scaling factor. In this particular case, I'm going to associate 50 miles per hour with a 2 centimeter long vector. So I'm going to start by drawing in the velocity vector that is generated by the engine. It's 200 miles per hour. To scale, that's going to be an 8 centimeter long vector. It's going to be at 30 degrees relative to the north. So I've had to have put in a little mini axis here so that I can use a protractor and get the angle right. By the time I get done, this is what I end up with. So the second vector is going to be the vector associated with the headwind. It was 50 miles per hour, which is going to translate into a 2 centimeter long vector. It's going to have to be put with its tail to the head of the first vector. I'm going to have to draw a little mini axis here so that I can use a protractor to get it down 20 degrees south of west. This is the west direction, this is the south direction. And so I can go ahead and draw in that second vector appropriately. When I get done, I will have the velocity vector associated with the engine added to the velocity vector associated with the headwind, and the resultant of the two will end up giving me the net velocity vector acting on the plane. To get the magnitude of the resultant, I'm going to use a centimeter stick. I'm going to measure the length of this resultant. Turns out that it's 6.6 centimeters. I'm going to take the 6.6 centimeters and I'm going to multiply it by the scaling factor, which was 50 miles per hour per 2 centimeters, and come out with 165 miles per hour. So apparently that's what the resultant speed of this plane is going to be as it's going into this headwind. I then need to know what the orientation of the plane is, in what direction, which is going to be an angle kind of a thing. So I'm going to need to use a protractor, and relative to the east, I'm going to have to go ahead and I'm going to have to measure that angle. And if you use a protractor, it turns out that it's right around 80 degrees, give or take. So in polar notation, the answer to our question is that the velocity of the airplane net is going to be 165 miles per hour at an angle of 79 degrees. So the steps are that you want to go ahead and you want to draw the vectors to scale, keeping their orientation dead on and using a protractor to make sure that you're accurate. You want to do the head-to-tail vector addition or subtraction. You want to come up with a resultant, and then you want to take that resultant and use a centimeter stick and your scaling factor to figure out what the net resultant vector's magnitude is, and then use a protractor to determine what its angular orientation is. And that, my friends, is it.